So what if I told you that the absolute smartest thing you can do to fix a broken AI model is to just, well, leave its underlying code completely alone?
Yeah, which is definitely not what most engineers want to hear.
Right. I mean, think about it. You are deep in the trenches, you're building a new AI feature, and the large language model you're using is just not cooperating. It's hallucinating facts. The formatting is a total mess.
Oh, always the formatting.
Always. And your immediate engineering instinct is to pop the hood and start altering the core machinery. You want to fine-tune it. But we are going to pump the brakes on that today.
We really have to, because it's an incredibly common instinct. In traditional software engineering, if a function isn't doing what you want, you just drop down a layer of abstraction, find the source code, and rewrite the logic.
Exactly. You fix the bug at the source.
Right. But applying that exact same logic to LLMs, like jumping straight to fine-tuning it, often leads developers into this just massive wall of technical debt.
And to figure out exactly why that happens, we are pulling from a pretty big stack of recent AI research papers, engineering blogs from teams who are actually scaling LLMs in production, and some, honestly, fairly painful developer postmortems.
Yeah, there's some real trauma in those postmortems.
Seriously! So today's deep dive is all about building a strict decision framework on when not to fine-tune large language models. We are laying out a map to basically save you from months of unnecessary maintenance.
And the very first step on that map, before we even discuss altering a model's underlying architecture, is a hard and fast rule found across all our sources.
Which is,
You must exhaust your prompting options first.
right?
Prompting is the simplest, it's the most cost-effective, and honestly the most maintainable approach available.
See, I know a lot of engineers, especially those coming from rigorous backend or systems backgrounds, they look at prompt engineering and feel a bit, well, skeptical.
Oh, absolutely.
It feels flimsy, like you're just typing English instructions into a black box and hoping for the best rather
Yeah.
than, engineering a deterministic outcome.
The skepticism makes total sense because we are used to compiling code, right, not negotiating with it. But modern foundation models have capabilities that developers often just severely underestimate.
Like what kind of capabilities?
Well, we talk about zero-shot and few-shot capabilities.
Ah.
Zero-shot meaning you ask the model to perform a task with absolutely no prior examples, just a raw instruction.
Okay, yeah.
And few-shot meaning you provide just, 3 or 4 highly structured examples directly inside the prompt.
Right.
The probabilistic engines behind these models are now so advanced that merely providing those few examples fundamentally alters the trajectory of the model's response. And you do that without changing a single neural weight.
It's essentially like interacting with a third-party API. I mean, skipping the prompt phase and jumping straight to fine-tuning, it's like trying to rewrite a third-party API's back-end source code just because you want a different date format in your response.
That is a perfect way to put it.
Like, you wouldn't fork an entire code base, maintain a custom branch, and deal with merge conflicts for the rest of eternity when the original API literally has a parameter you can just pass in the request header.
Exactly. And maintainability is
Yeah.
really the core issue there. If your prompt is just, a text string stored in a configuration file or a database, updating the system's behavior takes seconds.
Yeah.
You alter the text, you deploy the change, and it is live in production with zero compute cost. You can iterate dozens of times in a single afternoon.
Whereas fine-tuning.
Oh, fine-tuning, by contrast, requires curating a pristine data set, spinning up expensive GPU clusters, waiting hours for the gradient descent process to
They're
complete.
paying for all of it.
Right, paying for all of it. And then you have to deploy a massive multi-gigabyte model artifact to your infrastructure. The friction difference is just astronomical.
Okay, so you push the prompt to its absolute breaking point. But let's follow the framework here. Let's say we wrote the ultimate prompt. We used few-shot examples, defined the constraints clearly, structured the output format, and the model is still failing.
It happens.
It's hallucinating or missing the mark. This brings us to the diagnostic phase of the framework, right?
Yes.
We have to figure out the exact mechanism of the failure before deciding on the architecture to fix it.
And the sources outline a golden rule for this diagnostic phase.
Yeah.
You have to distinguish between a knowledge problem and a behavior problem.
A knowledge problem versus a behavior problem.
Exactly. This single distinction dictates your entire architectural path. So if the model lacks specific facts, let's say it doesn't know the parameters of your company's proprietary internal tool, or it's unaware of a news event that literally happened 3 hours ago, that is a knowledge problem.
And the solution to a knowledge problem is almost never fine-tuning. It's retrieval augmented generation, or E.
Right. Because on the other hand, if the model has the right knowledge, but it's using it incorrectly,
Like how?
like perhaps it writes code in a style that violates your team's specific conventions, or it consistently fails to make subtle logical judgments that are unique to your business domain.
Ah, okay.
That is a behavior problem. Fine-tuning is reserved for teaching the model how to act, not what to know,
People mix this up constantly. They try to use fine-tuning to teach the model new facts.
all the time.
If we think about this in terms of like onboarding a new junior developer to team, I think it becomes much clearer.
Oh, I like this analogy.
Right. So if that junior dev doesn't know the specifics of your messy legacy code base, you don't send them back to a 4-year computer science program to learn it.
No, definitely not.
That is fine-tuning. It's retraining their entire foundational understanding. Instead, you just give them the documentation.
Right, you point them to the wiki.
Exactly. You give them access to the internal wiki and the repository, that is RRA. You provide the exact context they need at the exact moment they need to execute the task. You only put them through rigorous fundamental retraining if their actual coding behavior or core problem-solving skills are fundamentally flawed.
And the underlying mechanism makes that onboarding analogy very literal. Because language models are probabilistic engines, right? They're not relational databases.
Right.
They generate text by predicting the most likely next token based on this massive web of associations in their neural weights. So when you try to force them to memorize a specific internal wiki page via fine-tuning, you are trying to bake hard facts into a fluid, probabilistic space.
Which sounds like a recipe for disaster.
It is. The model will often hallucinate anyway because it is still just guessing. But with ORAG, you inject the factual document directly into the context window at inference time, and you instruct the model to base its answers solely on that provided text.
It's reliable.
Completely reliable. And if the underlying facts change, you just update your database.
Okay, so RAG handles the knowledge. But if the model simply doesn't understand the nuance of how your application needs to respond, even when the facts are right there in the prompt, we've crossed the line into a behavior problem.
Yes, exactly.
We absolutely have to fine-tune, but our sources treat this as a last resort. We need to unpack the hidden costs here. What is the actual trap developers fall into once they decide to alter the weights?
Well, the trap is the ongoing technical debt, and it manifests in a few highly specific ways. The first major issue is this phenomenon in machine learning called catastrophic forgetting.
Catastrophic forgetting. That sounds, well, catastrophic.
Yeah.
What is the actual mechanism happening there?
So when you fine-tune a model, you use a process like gradient descent to adjust the internal weights of the neural network so it performs better on your new specific task.
Okay.
Let's say you take a general-purpose model that is great at casual conversation and writing Python, and you heavily fine-tune it exclusively on your company's highly rigid proprietary SQL dialect.
Right, because you really need it to write your specific SQL.
Exactly. But because the neural network's weights are shared representations of language, optimizing the pathways for your SQL dialect actively overwrites the weights that previously governed other tasks.
Wait, really?
Yes. You teach the model to write perfect SQL, and suddenly it entirely forgets how to write a basic Python loop. Or its conversational tone becomes totally robotic and broken.
Wow. It literally overwrites its own underlying capabilities to make room for the new behavior.
Exactly. The probabilistic pathways just get scrambled. So to manage a fine-tuned model, you can't just train it once. Every time you introduce a new behavior, you have to run extensive regression test suites to ensure you haven't destroyed its baseline intelligence.
That sounds exhausting.
It is a constant, fragile balancing act.
Okay, but I'm going to push back here for a second, though.
Sure.
Listening to this as a software engineer, managing regression tests and balancing updates just sounds like standard technical debt. I mean, we manage massive microservices architectures, complex CI/CD pipelines, version control. We do this every single day.
Yeah.
We know how to maintain complex systems. Why is managing a fine-tuned model any more burdensome than managing a standard software stack?
The difference lies in the stability of your foundation. With a microservices architecture, you own the core logic. Frameworks update, sure, but your static code remains yours.
True.
In AI, your foundation is the base model itself, and it is evolving at an unprecedented pace, completely outside of your control.
Oh, I see where this is going.
Yeah. Let's say you spend 3 months painstakingly curating a dataset, managing catastrophic forgetting, and fine-tuning an open source model. We'll call the base model version 1.0.
Okay.
You get your custom version working perfectly in production.
It does exactly what the business needs. It's beautiful.
But a month later, the AI provider releases version 2.0 of that base model. And version 2.0 is vastly superior out of the box. It has a larger context window, better reasoning, it's cheaper to run.
And you obviously want to use it.
Right. But if you want to take advantage of that incredible new baseline intelligence, you cannot just port your fine-tuned weights from version 1.0 over to version 2.0.
Because the architecture of the model itself has changed.
Exactly. The parameter count might be different, the attention mechanisms might have shifted, the network layers are different, the mathematical matrices literally do not multiply together anymore. They are fundamentally incompatible.
Oh, man.
To upgrade to version 2.0, you have to start entirely over. You have to take your training data, rebuild your pipelines, and run the expensive fine-tuning process from scratch on the new base model.
Wow.
And you will have to do this every single time a major base model update occurs.
So you are basically tethered to a treadmill.
Exactly.
If you fine-tune, you are committing your engineering team to rebuilding your custom layer from scratch every time the AI industry takes a step forward. That is a massive hidden cost.
It really is. And that leads directly into the second major warning from the sources, which they call the evaluation trap.
The evaluation trap.
Yeah, it's a trap that creates a false sense of security right before you deploy to production.
How does that work? Is this related to how we test the model after it's trained?
It's all about the training and testing data distribution. So when you fine-tune, you hold back a portion of your data, say 20%, to use as a test set to evaluate the model's new behavior.
Right, standard machine learning practice.
Right. And often, a fine-tuned model will score incredibly well in that test set, hitting 95 or 99% accuracy. The engineering team sees those numbers and assumes the model is robust and ready for the real world.
But the test set is drawn from the exact same highly curated data pool as the training set.
Yes. The exact same distribution. The prompts in the test set represent the exact same types of inputs, phrased in the same tone, collected under the exact same conditions.
So what's the problem?
What the model has actually learned is not a generalized understanding of the behavior you want. It has just aggressively overfit to the specific grammar and patterns of your training data.
Oh, I see. So in production, when a real user types in a prompt using weird slang, no punctuation, or some compound sentence structure that just wasn't represented in your pristine training set.
The probabilistic pathways hit a dead end.
Oh.
Because the model has been so narrowly optimized for your specific distribution, its generalized reasoning is compromised. It becomes brittle.
That makes a lot of sense.
It will hallucinate, format the output incorrectly, or fail spectacularly on inputs that a standard, non-fine-tuned base model would have handled effortlessly with a good prompt.
Because you essentially trained it to pass your specific test, destroying its ability to adapt to anything else.
Precisely.
Okay, so if prompting is our first line of defense, RI is the solution for knowledge, and fine-tuning is this heavy, fragile burden full of traps that we only use as an absolute last resort.
How did the best engineering teams actually build reliable AI systems at scale? Well, the consensus across the engineering postmortems is that the ultimate production architecture does not rely on just one of these methods.
Right.
The most robust AI systems running in production today layer all three techniques together.
They combine them.
Exactly.
So you use RAG to inject the accurate, up-to-date knowledge into the system at runtime. You use advanced prompting techniques to establish the constraints, enforce the formatting, and build the control mechanisms. And then you reserve fine-tuning purely for the underlying style, tone, and complex judgmental behavior that prompting simply cannot stabilize across edge cases.
That is the trifecta.
I love that because that maps perfectly onto standard web architecture.
Yep.
We are literally just talking about the separation of concerns in a multi-tier tech stack.
Yes.
Think about it. RAG is the database layer. It is the query pulling the raw records and facts.
Right.
Prompting is the controller logic. It takes the raw facts, applies your application's constraints, formats everything cleanly, and routes it.
Exactly.
And then fine-tuning is your core business logic. It defines the unique value proposition and the deep underlying rules of your specific application.
The separation of concerns is exactly the mechanism that makes it work. I mean, if you put your database queries inside your core business logic, or your formatting rules inside your database, your traditional software system becomes unmaintainable.
Total spaghetti code.
Exactly. And the exact same principle applies to AI. If you try to use fine-tuning to memorize database facts, or use prompting to force a model into a behavioral paradigm it just wasn't built for, the system breaks down.
Yeah.
By layering them correctly, RAG for knowledge, prompting for control, fine-tuning for behavior. You distribute the load. The system becomes scalable, and, honestly, more importantly, you can isolate and debug failures much faster.
It totally demystifies the whole process. It takes this entirely new probabilistic paradigm of large language models and grounds it back in the fundamental software engineering principles we already rely on every day.
Which is really the only way to move AI out of the prototype phase and into reliable enterprise-grade production.
All right, let's summarize this decision framework so you have it locked in the next time you're staring at a failing model output. Rule number 1, always try prompting first.
Always.
Exhaust zero-shot and few-shot capabilities before you do anything else because it is the most maintainable path.
Rule number 2, run the diagnostic. Determine if you are facing a knowledge problem or a behavior problem.
Right. If the model lacks facts, it's a knowledge problem. The solution is RG. Inject the documentation at inference time. Do not try to bake facts into neural weights.
And if the model has the facts but is failing at nuanced, domain-specific judgments, you have a behavior problem.
This is when you consider fine-tuning. But you enter that process fully aware of the technical debt. You manage catastrophic forgetting, you prepare to rebuild your pipeline for the next base model update, and you aggressively test against out-of-distribution, real-world data to avoid that evaluation trap.
Exactly.
And the ultimate goal is to architect a multi-tier system where ROG, prompting, and fine-tuning each handle their specific layer of concern.
That's the playbook.
Now, you might be sitting there thinking, all right, I understand that prompting is the first line of defense, but how do I actually engineer a prompt robust enough to avoid the need for fine-tuning in the first place?
It's a great question.
Our sources have a lot to say about that. And tomorrow, we are diving deep into the anatomy of prompt engineering. We will look at why the exact same model can produce entirely different logical outcomes based purely on the structural constraints of the words you feed it.
It really moves far beyond just, typing instructions. There is a deep mechanical structure to how these models parse context windows that we will completely break down.
It's going to be fascinating. But before we wrap up this deep dive into the fine-tuning framework, there is a final, rather provocative thought from the sources to leave you with.
Oh, yeah.
We discussed how one of the most painful costs of fine-tuning is that your custom weights become instantly obsolete the moment a vastly smarter base model is released.
The treadmill of base model updates.
Right, the treadmill. But think about the trajectory of those base models. Every generation has a larger context window, deeper out-of-the-box reasoning capabilities, and just a much better ability to follow complex instructions via in-context learning.
They are getting so incredibly capable.
So if foundation models continue to get exponentially smarter and more adaptable with every single release, will the need for fine-tuning eventually disappear entirely?
It's a real possibility.
Are we moving toward a future where the underlying probabilistic engines are so inherently capable that software engineers will only ever need a vector database for agri and a brilliantly engineered prompt?
That would definitely change the entire industry.
It's definitely something to mull over the next time you feel the urge to start tweaking neural weights. We will catch you on the next deep dive.